So, good evening, everyone. Welcome to the third problem solving session for the course Environmental Remediation of Contaminated Sites. So, we will wait for a couple of minutes for others to join and then we will start. So, we can start now. So, good evening, everyone. Welcome to the third problem solving session for the course Environmental Remediation of Contaminated Sites. So, I am one of the TA for this course. My name is Asma Parveen and I am a PhD scholar at IIT Kanpur. So, for this course, I am taking problem solving sessions on every Sunday from 6 to 8 p.m. So, like previous weeks, what we will do is like we will go briefly through the lecture slides, see the important concepts and formulas on which we are going to solve the present questions, and then we will move to the assignment questions. So, first, let me share my screen. So, before this, I can see one hand is raised by Yellow Him. So, do you have any question or doubt? Okay. I think there is no question, so let me first share my screen. So I think I'm audible. Yes. So in the first week and first week was about introduction, in which introduction about hazardous waste management. was given, and what are the rules for it, and some of the lecture were also on the detail of the hazardous waste management rules 2016. And then in week 2 we have discussed about risk assessment, like how to do the risk analysis for carcinogenic and non-carcinogenic pollutants. And then we have seen numericals based on risk, hazard index, and hazard index or hazard quotient, that is for non-carcinogenic compounds. And for carcinogens we have seen the risk, and we have solved few numericals on this concept also. So week 3 is about uh, from here, from this week we will be discussing about the various methods for remediation of the contaminated soils or aquifers. So this week it is about pump and treat method. So in pump and treat method, what is done is like the water from the aquifer is pumped, taken out, and then it is treated. And then after treatment, it is either re-injected in the aquifer or it is used for some other purposes. So this table shows the treatment technologies, and different screening methods have been used based on the cost and based on the type of contaminants. So next, so the contaminants in the groundwater can be present in the aqueous phase, like it can be present in the water or it can be present in the soil or sediments. So first is the plume containment. So in plume containment, what is done? It is used to isolate the contaminant plume from normal groundwater flow so that the water in the groundwater is not polluted, and it prevents the plume from reaching another aquifer. Various various wells or other methods can be used to stop the plume from spreading. So next, uh, s- uh, design for the extraction wells was discussed. So based on these designs, we will try to solve few numericals based on these extraction wells design. Let me show the final. So this is the graph for two wells. So the distance between each well and how much water will be taken out in the upper upstream side and the downstream side of the wells, and so on. So next was continuation of this. So this formula is used to find out the drawdown, and it is based on the distance from the center of the line of the well to the distance where we have to calculate the drawdown. And next is the storage coefficient, transmissibility. So this is the product of hydraulic conductivity and saturated thickness. So that is, it is the property of the aquifer, and Z is the drawdown and T is the time since pumping began. So through this formula we can find out the drawdown in the aquifer. So there are a few approximations for a well function. So if we use the velocity as between 0 to 1, then we can use this formula. And okay, next is the spreading of the contaminant. So it can be either by advection or dispersion. So advection is when there is a flow in of either flow of water, and if we take in air, then there is a flow of air in one particular direction, and because of that flow, the pollutant or contaminant spread. And next is the dispersion. So dispersion is because of the difference in the concentration between two places. So from higher concentration to lower concentration. So because of this concentration gradient, the pollutants spread. So next is simulation to capture front of the plume. So here the extraction will be digged or installed to take out the contaminated plume from the aquifer. Okay, let's move. Pictures changed. So, depending upon the type of pollutant, so the contaminant or pollutant, it can be present in the aqueous phase, like it will be only present in the dissolved phase, or it can be adsorbed, or it is better to say sorbed on the soil or sediment particles, or it can be a non-aqueous phase liquid, which can be either at the top or at bottom of the aquifer. So from this graph, we can see that when the pumping is started, so the concentration of the pollutant decreases, but after some time we can see that there is some rebound and there is increase in the concentration of the pollutant when pumping is stopped. So this like we are taking out the water from the aquifer, so the contaminated water is taken out. That's why the concentration will decrease. But as soon as the pumping is stopped, if the pollutant is adsorbed on the soil particles, or if there is some other storage of the pollutants, then because of equilibrium, the pollutant from the soil or sediments will again start to dissolve in the water, and slowly the concentration will increase and it will saturate to nearly a constant concentration after equilibrium is reached. So not only we have to consider the removal of the polluted water, but we will have to see whether the pollutant is sorbed on the soil or sediments, or whether we have some non-aqueous phase liquid which can also store the pollutant, or which can also sorb the pollutant, and with time it will slowly release the pollutant in the aquifer. So these were the case for that. So here we can see that because of the density, so the pollen NaPl can be a low density, so it will float at the top of the water. It can be have high density, so it will go at the bottom of the aquifer, and it will settle there, and it will act as a storage for the pollutant. So and it will take hundreds of years to remove the pollutant from the aquifer if we do the treatment through pump and treat method. So these are the pictures through which mechanism has been explained. Okay. So the type of soil or cell present in the aquifer will also determine the extent of the pollutant spreading. Like if we can see that in sand, the hydraulic conductivity is higher, so that's why it will have higher velocity. And in the clay, it has lesser hydraulic conductivity, so the velocity profile will be less. And here, since the velocity is less, so advection will not play role. Diffusion will be dominant in this layer, and in the gravel layer again velocity will be high, and that's why convection, or we can say advection, will be dominant in the gravel layer. So depending, so we can see that there are different layers in the aquifer, so different mechanism will be dominant process that will lead to the spread of the pollutant. So again, this lecture was also about derivation of the formula which we will be using to find out the time required to treat the polluted water. So we will see there only. So I think this is also on. So this is also the derivation of the formula for the retardation factor, which will be finding out in the numericals. So, and for the next week is about permeable reactive barrier. So, sir has also given a brief introduction about permeable reactive barrier. So, let's move directly to the questions. So, we will discuss all the formulas in the while solving the numericals. So, just give me a minute. So the first question is, as per the simulation by Zevendel et al., what will be the capture zone width at the wells and the capture zone width far upstream of the wells respectively, given that there are n wells. So these formulas were discussed that if there are n number of wells, so what will be the capture zone width at the wells and at the far upstream of the wells. So what I will do, I will give you all 3 minutes. Just take your time and write the option which you think is correct in the chat box, and then we will discuss. So the capture zone width at wells. So for one well, it's 0.5 Q by BU, and for N wells, it is zero point 0.5 multiplied by NQ by BU. And the capture zone width far upstream of the wells, it is given by, for one well, it is given by Q by BU, and for N wells, it will be NQ by BU. So B will be the correct answer. So the capture zone width at the wells will be 0.5 NQ by BU, and capture width far upstream of the wells will be NQ by BU. So now let's move to the next question. So the next question is, with respect to the calculation of drawdown, an optimum number of wells required to treat a contaminated plume by pump and treat method, select the correct option. A. If we increase the pumping rate, the drawdown will increase. Transmissivity, hydraulic conductivity, and thickness of saturated soil are required. Storage coefficient and time since pumping began are required. Well function is required, and it depends on the velocity of the water, or E, all of the above. So we have to select out of the five options which one is the correct option. So again, I will give you all 1 minute. Just take your time, write the option in the chat box, and then we will discuss. So let's see. I have got one answer as E, so E is the correct answer. So let's see which of the following are the correct. So the well flow or drawdown is given as. So this is the equation for drawdown calculation. So for pump and treat methods, we pump the water from the aquifer. So we need to calculate the drawdown, and we need to know the various characteristics of the aquifer. So first option is, if we increase the pumping rate, the drawdown will increase. So from this equation, we can see that as we are increasing the Q, so Z is directly proportional, so Z will increase. So first option is correct. So the next question is, transmissivity, hydraulic conductivity and thickness of saturated soil are required. So here we can also see that we need to find out the transmissivity. So this option is also correct. Next is the storage coefficient and time since pumping began are required. So this is also correct. We need to find out the time since pumping began and storage coefficient also. So because uh, uh, U is the function of distance from the center of the well to the point where a drawdown is calculated, SC by 4 capital T into T, where SC is the storage coefficient and small t is the time after which the pumping has been begun. So storage coefficient and time since pumping began as required. So this is also correct. And the next option, that well function is required and it depends on the velocity of the water. So we have seen in the slide that well function is required and well function is the function of the velocity of the water. So depending upon the velocity, there are different well functions. So this option is also correct. So E is the correct answer, that all of the above. So all the four options given are correct with respect to pump and treat method. So E will be the correct answer. Now let's move to the next question. So the question is, select the correct statement. First is, if KOW of the if the octagonal water partitioning of the contaminant is low, pump and treat is a good option. Next option is, if contaminant is hydrophobic, pump and treat is not a good option. C. As per Zevendel et al., the pumping rate to capture the plume is twice the groundwater flow rate through that cross section, or D. All of the above. So again, I will give you all 3 minutes. Just take your time and write the option in the chat box, and then we will discuss which of the following are correct. So let's see. I got one answer as D and one as C. So D is the correct answer. So if KOW of the contaminant is low, pump and treat method is a good option. So this one is correct. So if the octanol water partition coefficient will become, so the contaminant will be more in water phase. So that's why it will be more in aqueous phase. So pump and treat method will be a good option. Next is if contaminant is hydrophobic, pump and treat is not a good option. So this is correct because majority of the contaminant will not be present in the water. So it may be present in the sediments or NaPl components present in the aquifer. So pump and treat will not be a good option. Next is as per Zavendel et al., the pumping rate to capture the plume is twice the groundwater flow rate through that cross section. So this statement is also correct that we take some factor of safety. So this is and this factor of safety is that we capture the we take out twice the groundwater flow through a particular cross section, and then we pump the two times the water from that cross section section, and this is a factor of safety which we take in the pump and treat method. So D will be the correct answer, that all of the above statement are correct. So now let's move to the next question. So this is a numerical type question. So the question is, groundwater at a site is contaminated with dichlorobenzene with a concentration of 0.2 ppm. The volume of the contaminated soil is 80,000 cubic meters. The pumping rate of the water is 1000 liter per hour. The porosity of the soil is 0.5. Calculate the time required in days to pump the contaminated groundwater. Assume that the concentration in the pumped water is 30% of the concentration in the contaminated plume, and assume the contaminant is present only in the aqueous phase. So we have to find out the time required to pump this much concentration of the dichlorobenzene. So we have to find out the time. So I will give you all 5 minutes. Just take your time, solve this question, and write the value which you are getting in the chat box. And then we will see how to solve this one. So let's see how to solve this question. So I got one answer as 5500 days. Uh, so 5500 is not correct. Actually, it is 5555 days. So let's see. So we know that time required to pump the contaminant is given as mass of contaminant divided by pumping rate into concentration of contaminant in pumped water. And the mass of contaminant, it will be given as porosity into volume into concentration of contaminated plume divided by pumping rate into concentration of contaminant in pumped water. So we have porosity as 0.5. So porosity is given as 0.5. We have the volume of contaminated soil as 80,000 cubic meters, and we have given the pumping rate as 1000 liter per hour. So we will convert this into meter cubes per hour. So 1000 divided by 1000 to convert into meter cubes. So it will be 1 meter cube per hour. And so time will be porosity into volume divided by pumping rate is 1. Concentration of contaminant is, I think, uh, so it will be so here the concentration of the contaminated plume and the concentration of contaminant, this will cancel out. So it will be time required will be epsilon V by Q. So we have 80,000 divided by 1, and one statement is given that Assume that the concentration in the pumped water is 30% of the concentration in the contaminated plume. So it will be 0.3 into we have concentration of zero point 0.2 and above also it will be zero point 0.2. So this will cancel out. So let me calculate. So it's coming out to 133.33 R. So convert it into days. We will divide by 24. So we are getting 5555.55 days. So 5555 days is the correct answer. So we are given the volume of the contaminated soil, then we have given the concentration of the dichlorobenzene, and we have been given the pumping rate, we have been given the porosity. So we have to calculate how much time will be required to pump this water. So we know that the time required is given by this formula, and this formula is dependent on this, like the concentration of contaminated plume. It cancels from the numerator and denominator, but here it was given that nearly 30% of the concentration is coming out in the aqueous phase. So that's why at the denominator we will multiply the concentration that is coming out as 30%, that is zero point 0.3, and we will get, after solving this value, we are getting 5555 days. So this is the correct answer. So I hope this question is clear to all you all. So if you have any doubt, you can ask. Okay, let's move to the next question. So again, it is a numerical based question. So the question is, a site is contaminated with TC, that is trichloroethylene. So the source zone is 350-meter long, 80-meter wide, and 20-meter deep. Organic matter fraction is 4%. Soil water partitioning coefficient is 200 liters per kg. Porosity is 0.5. Bulk density is 1.73 kilogram per liter. And we have to find out the value of the retardation factor. So again, I will give you all 5 minutes. Just take your time, try to solve the question. Write the value which you are getting in the chat box, and then we will see how to solve this question. So let's see how to solve this question. So retardation factor is given as 1 plus Kp rho B by epsilon, where epsilon is the porosity, rho B is the density, bulk density of the soil, and Kp is the distribution coefficient, which says how much contaminant is adsorbed to the soil particles. So, and it depends upon the organic fraction of the soil. So, Kp is given as KOC into FOC. So, let's see how to solve this. So, we have been given organic matter fraction. So, organic matter fraction is given as 4%. So, that will be 0.4. We have been given the soil water partitioning coefficient. KOC is given as 200 liters per kg. We have porosity as 0.5, bulk density as 1.73 kg per liter. So we can find out the distribution coefficient as KOC into FOC. So we have KOC as 200 into FOC as 0.4. So it will be 8 liters per kg. So because we have 200 liters per kg, so 200 into 0.4 is 8 liter per kg. So now the retardation factor, we just have to put the values of everything. It is 1 plus Kp. Kp we have calculated as 8. We have the bulk density of soil is 1.73 and the porosity is I think 0.5. So let's solve this and find out the retardation factor. So it's coming out to be 28. 28.68. So this is the retardation factor. So I hope the question is clear. So if you have any doubt, you can just unmute yourself and ask. So let's move to the next question. So question number 6 is the retardation factor was calculated as per the site conditions of 4 contaminated sites. Site A, B, C, and D have 4 retardation factors of 2.34, 6, 8, and 1.67 respectively. The sites are treated by pump and treat. Select the case in which rebound and tailing will be the most probable to least probable. So based on the retardation factor, we have to predict which of the sites will have most probable and least probable rebound and tailing. So again, I will give you all 3 minutes. Just take your time and write the option in the chat box and then we will discuss. So let's see which of the following is the correct option. So based on the retardation factor, so higher the retardation factor, more will be the rebound and tailing. So we have maximum retardation factor in site C. So most probable rebound will be seen in site C. Then we have retardation factor of 6, which is in site B. Then we have a retardation factor of 2.34, which is in site A. And lastly, it is 1.67, that is site B. So maximum rebound and trailing will be seen in site C, followed by B, A, and D. So B is the correct answer. Now let's see and let's move to the next question. So this is a numerical type question. So the question is, a site is contaminated with PCE with an aqueous concentration of 15 gram per meter cube. The source zone is 200-meter long, 50-meter wide, and 10-meter deep. Organic matter fraction is 1%. Soil water partitioning coefficient is 126 milliliters per gram. Porosity is zero point 0.4. Bulk density of soil is 1900 kg per meter cube. And pure NaPl, that is non-aqueous phase liquid, 1623 kg per meter cube, is present in 3% of the pore space. So next we have to calculate the retardation factor. So again, I will give you 5 minutes. Just take your time and try to solve this question, and then we will see what is the correct value. So this is the expression for retardation factor when any NaPl is present in the aquifer. So let's see what is given. So we have been given the concentration of Pc in aqueous phase, which is 15 gram per meter cube. So we will convert it into grams per liter. So it will be 15 upon 1000 gram per liter. So we have been given the organic matter fraction is 1%, which will be 0.01. We have been given the soil water partitioning coefficient is given as 126 ml per gram. Next is given a porosity is 0.4. Bulk density of soil is 1900 kg per meter cube, and density of NaPl is 1623 kg per meter cube. So retardation factor. So before that, let's find out Kp, partition coefficient. So it is given as FOC into KOC, that is 0.01 into 126, which will be 1.26 ml, ml per gram. So now retardation factor will be 1 plus bulk density of soil is given as 1900 kg per meter cube. So we will convert 1900 kg per meter cube into kg per liter. So we will divide by 1000, so that will be 1900. Okay. So Kp is 1.26 into 1900 divided by 1000 divided by 1 minus S. S is the percentage of the pore space filled with NaPl. So S is given as 3%. So that will be 0.03. So 1 minus 0.03 into epsilon, porosity is 0.4. Plus so fraction of percentage of pores filled with NaPl is 0.03 into density of NaPl, which is 1623 kg per meter cube, divided by 1 minus S multiplied by concentration of Pc in aqueous phase, which is 1500 grams per liter. So it will be 15 by 1000. So on solving, we will get the retardation factor. Let's see what value it is coming. So on solving this, we are getting the retardation factor is 3353.47. So this is the retardation factor when some NaPl is present in the pore space. So we can see that with the presence of NaPl, the retardation factor has increased. And also with the partitioning of the pollutant between soil and aqueous phase, the retardation factor will be higher as compared to when the pollutant is present is in only the aqueous phase. So now let's move to the next question. Okay. So question number 8 is a site is contaminated with PCE with an aqueous concentration of 15 gram per meter cube. The source zone is 200-meter long, 50-meter wide, and 10-meter deep. Organic matter fraction is 1%. Soil water partitioning coefficient is 126 ml per gram. Porosity is 0.4. Bulk density of soil is 1900 kg per meter cube. Pure NaPl density is believed, and pure NaPl density is 16,023 kg per meter cube, and it is believed that it is present in 3% of the pore space. So the total mass of contaminant in tons is, so everything is given, we have to calculate the mass of the contaminant. So again, I'll give you all 3 minutes. Just take your time. Please try to solve these questions because similar questions will be there in your assignment and the questions which will be on the final exam. So please try to solve the question and write the value which you are getting in the chat box. Okay, let's see. So, the formula to calculate the mass of the contaminant will be this, that the mass of the contaminant will be 1 minus S epsilon V C naught. So, where S is the fraction or percentage of the pores filled with NaPl, epsilon is the porosity, V is the volume of the soil or sediment, C naught is the concentration of the pollutant in aqueous phase, rho B is the bulk density of the soil, Q is the fraction of the contaminant which is adsorbed on the sediment or soil. V is again volume of the soil. And S is again percentage of the pores filled with NaPl. Epsilon is the porosity. V will be the volume. And rho NaPl is the density of the NaPl. So I think everything is given. Let's first write what is given and then we will put the values. So we have been given S is I think 3%. So 3% of the pores is filled with NaPl, so it will be 0.03. Epsilon is I think zero point 0.4. Yes, porosity is zero point 0.4. So we need to calculate the volume of the soil. Length is 200 meter, width is 50 meter, and depth is 10 meter. So we will calculate the volume from here. So volume will be L into width into depth. So length is 200 meters into 50 multiplied by 10 meter depth. So it will be, I think, so 1 lakh meter cube or 100,000 meter cube. And partition coefficient will be FOC into KOW. Sorry. So fraction of organic matter fraction is 1%. So 1 by 100 into soil water coefficient is 126 ml per gram. So it is 1.26 milliliter per gram. So next we will convert it into liters per kg. So to convert milliliters to liter we will divide by 1000, and to convert gram to kg we will again divide by 1000. So everything will cancel out and it will be 1.26 liter per kg. Now Q, the fraction of or how much contaminant is adsorbed or sorbed on the soil per kg of the soil. It is given as Kp into C naught. This is the partitioning coefficient. So Kp is 1.26 into, so this is liter per kg, and the concentration of contaminant is 15 gram per meter cube. So to convert the meter cube into liters, we will divide by 1000, and to convert the grams into kg, we will again divide by 1000. So now this will be kg per liter. So everything will be cancelled out and it is coming out to be 18.9 into 10 raised power minus 6. So I think we have calculated everything. So the total mass of the contaminant will be 1 minus S. S is 0.03 into epsilon is zero point 0.4. Contaminant concentration in this in aqueous phase is given as 15 gram per meter cube. So it's better to convert into uh, grams per liter. So 15 upon 1000 plus density of the soil is given as 1900. Q is given as 18.9 into 10 raised power minus 6. And volume we have calculated as 100,000 meter cube. Plus we have fraction of pores filled with NaPl is 0.03. So S is 0.03. Porosity is 0.4. Volume is 100,000 meter cubes. And density of the NaPl is 1623. I think we have calculated everything in meter cubes and sorry, liters and grams. So let's solve this and find out what value we are getting. So I forget to multiply volume in the first term. So 1 minus 0.03, epsilon is 0.4, volume is 100,000 meter cubes, and C naught is 15 by 1000. So on solving the first term, we are getting 582 plus second term we are getting as 3591 plus so these values are in kg. So to convert it into tons, we will divide by 1000. So let's first calculate how much kg we are getting. So it's 582 plus 3591 plus 1947600. So it's 1951773 kg. So we will divide it by 1000 to convert into tons. So it is 1951.773 tons. So this much is the amount of total mass of the contaminant that PCE which is present in this given volume of the soil. So I hope this question is clear. So if you have any doubt, you can ask, or else we can move to the next question. Okay, let's move to the next part. So question number 9 is select correct option regarding tailing observed while pumping out contaminated groundwater. A. Tailing is observed because the flow velocity at periphery is higher than at center. B. Tailing is observed because the flow velocity at the center is relatively higher than that at the periphery and resorption of contaminant from media. C. Tailing may be observed because the flow velocity is uniform throughout. Or D. None of the reason causes tailing. So we have to select the reason which causes the tailing while pumping the contaminated groundwater. So again, I will give you all 3 minutes. Take your time and write the option in the chat box, and then we will discuss. So let's see which of the following option is correct. So first option is tailing is observed because the flow velocity at periphery is higher than at the center. So no, the velocity is higher at the center than the periphery. Sorry. So tailing is not because of the flow velocity. Next question is, next option is tailing is observed because the flow velocity at center is relatively higher than that at the periphery and desorption of contaminants from media. So this option is correct, that the velocity at center is higher than the periphery, and the contaminants gets desorbed from the surrounding media. That's why tailing and rebound is seen in the aquifers. And next option is tailing may be observed because the flow velocity is uniform throughout. So the statement is not correct. Flow velocity is not uniform. So B is the correct answer. That tailing is observed because of the desorption of the contaminants from the media and because of the higher velocity at the center as compared to the periphery. So now let's move to the last question. So the question is, under what circumstances might there be a resurgence in the concentration of contaminants in groundwater? A, presence of DNAPL or LNAPL. B, soil stratification conditions. C, homogeneous condition with media that has high organic content. Or D, all of the above. So again, I will give you on 3 minutes. Please write the option which you think is correct in the chat box. So let's see which is the correct option. So resurgence in the concentration of contaminants can be because of the DNAPL or LNAPL, that is the dense non-aqueous phase liquid, or uh, uh, light non-aqueous phase liquids. Next is soil stratification conditions. So this is also correct, that resurgence can be because of this. Option C is homogeneous conditions with media that has high organic content. So because of organic content also, resurgence in the concentration of contaminants can be seen. So D, all of the above is the correct answer. So these were the questions based on week 3 material. I hope all the questions are clear to you. So if you all have any doubt, then you can ask, or else we can end the session here. Okay. Okay, I think there is no question. So we can end the session here. So thank you so much for joining. Have a nice day. We will meet on next Sunday from 6 to 8 p.m. Thank you.